Hello, we're back for another Physics 1151 lecture. Today we move on to Chapter 18, which is Macroscopic Description of Matter. We're going to just briefly cover a little bit the difference between solids, liquids, and gases, and then we're going to move on to discussion of some of the variables that are used to describe these substances. Mass, moles, density, and then we move on to temperature. So I make no claim that every topic we're going to cover in the course is equally interesting, and so although this is important, it is a bit dry, and you may want to stop your video and get a cup of coffee and come back and continue, but we'll get through it. So. Solids, liquids, and gases. Okay, you've covered all of these. Okay, liquids and gases we collectively call fluids, and solids we covered pretty much throughout the course until chapter 14. So they differ in the how tight the molecules are bound together. And so in a solid is rigid. The molecules are very tightly bound, they're packed together. There's very strong bonds between the atoms and the molecules. And if you ever try to compress a solid, it's impossible, right? They don't compress. Um, and so solids are very rigid and packed in. If you melt the solid by supplying some thermal energy and you melt it and it forms a liquid, the molecules are able to move a little bit. They're still tight, they're still bound to one another, but they're not as bound as in a solid, and so the molecules are able to move relative to one another, and so a liquid can flow. But it's still pretty close to incompressible, and that's just due to the fact that there are still some weak bonds between the molecules. You get to a gas, suppose you boil the liquid, and when you boil it into the gas, you basically break these bonds between the molecules, and the molecules are move pretty much independently. So you can think of them as a bunch of balls bouncing back and forth along and smashing into the walls of the container, but very little interaction with the other molecules except when they collide. And because the gas molecules are on average much further apart than they are with a liquid or a solid, gases are easy to compress and they also flow. So collectively, liquids and gases are called fluids because they flow, and they differ in solids mainly by how packed in the molecules are. So in any system or in any substance, there's variables that are used to describe the system at the macroscopic level. And so we've dealt with most of these already. So mass, volume, mass density, pressure, and temperature. And these are what are called state variables. In other words, for a given state of the system, they're well defined. And so in thermal equilibrium, which we're going to be getting into in a little bit, for example, if a gas is in thermal equilibrium, the variables such as pressure, temperature, and volume are constant in time. Now, before we get into this topic, we need to describe some of the variables. We've already described pressure, and we've already described volume, and we've already described density. But there's some different units that some of these variables can be used depending on the system. And so we're going to start with mass. And we've already talked about mass, right? Mass is basically a measure of how much of a substance that there is. And for macroscopic objects, the typical unit to describe mass is the kilogram. So at the atomic level, there are a few other ways that we can describe, how much of a substance there is. We can describe in terms of moles, and if you've taken chemistry, you've dealt with this. We can describe it in terms of the molecular mass, which is how much mass each molecule or atom is. And so when we get to these units, we have to introduce something called the atomic mass unit. And one atomic mass unit is roughly the mass of a proton or a neutron. It's 1.66 times 10 to the negative 27 kilograms. And for the most part, so to find the atomic mass of any substance, we can just look it up in the periodic table. This number right below the symbol for hydrogen and for lithium and sodium is what's called the atomic mass. And if you look, it's nearly equal to the sum of the number of protons plus the sum of the number of neutrons in the atom. I say nearly, but not exactly. So hydrogen, for example, has 1 proton and 0 neutrons. And so the atomic mass, it's 1.07007 atomic mass units. Lithium has 3 protons and 3 neutrons. And so the sum of protons and neutrons is 6. And the atomic mass of lithium is 6.94, which is close but not exactly equal to 6 atomic mass units. Now, to determine the mass of a single atom, we simply multiply the number of atomic mass units. So, for example, beryllium has 9.01 atomic mass units, and each mass unit corresponds to 1.66 times 10 to the negative 27 kilograms. And so you multiply the number of mass units by 1.66 times 10 to the negative 27 kilograms, and you get the mass of a single beryllium atom. So to get the atomic mass, we simply look up at the periodic table, and it's given below the symbol and below what's called the atomic number. Now, related to the atomic mass is the molar mass, or the number of moles of a substance. And so with any substance, if I say I have 1 mole of lithium, for example, I have 6.022 times 10 to the 23 molecules. And so that's the number of molecules or the number of atoms in a mole of any substance, whether it be beryllium, lithium, hydrogen, helium. If I say I have a mole of a substance, I have 6.022 times 10 to the 23 molecules. And we call this constant Avogadro's number. And so we denote it by N. Big N is the number of molecules. That's the symbol we'll be using. And A is for Avogadro. And so Avogadro's number is 6.022 times 10 to the 23 molecules per mole. Okay. Now, molecules aren't a unit, so a lot of times you'll see it given in units of inverse moles or 1 over moles. But I like to include the molecules, even though it's not a unit, just for bookkeeping purposes and for dimensional analysis. And so if we know the number of moles, which we're going to call little n, and we have the number of atoms or molecules, which is big N, to go back and forth, we simply multiply or divide by Avogadro's number. And so, for example, if I have 2 moles of a gas, and each mole corresponds to Na, number of molecules, I have 2 times Avogadro's number, which is 12 times 10 to the 23 molecules in the atoms in the gas. Okay, so that's how we convert back and forth between describing a gas by its number of molecules or the number of atoms or the number of moles. And this is important because a lot of the chemists will often talk in terms of the number of moles of a substance, and the physicists will talk in terms of the number of molecules or atoms. And to go back and forth, we just use Avogadro's number, which is molecules per mole, to relate them. And this is where including the molecules and the molecules per mole along with dimensional analysis can be used to remember whether I divide or multiply by Avogadro's number in going from moles to atoms. For example, N is in moles, Avogadro's number is molecules per mole, and when I multiply them together, that gives a dimension of molecules or atoms. Now it also turns out that the mass of 1 mole of a substance has the same numerical value as the atomic or the molecular mass of the substance. So for example, if you look at lithium, the atomic mass of lithium is 6.941 atomic mass units. Okay? Well, 1 mole of lithium therefore weighs 6.941 grams. And so the atomic mass number of a given substance also corresponds to the mass of the substance, how many grams corresponding to 1 mole. Okay? So it's easier sometimes to just do an example, and so we will do that. After first noting that here's a periodic table, and in most cases, the atomic mass, for example, carbon has 6 protons plus 6 neutrons, and the atomic mass is exactly 12 AMUs. Some atoms it's a little bit different, like zinc or copper. And when you get to the bigger ones, it becomes a little bit greater than 2 times the number, or the number of protons plus the number of neutrons. Okay, so now let's do an example here. So suppose we have a CO2 gas molecule. So in the first step, we want to know what is the mass of CO2, of 1 CO2 gas molecules in units of atomic mass units. Okay, and when we get to molecules, it's pretty simple. We look up how many carbon atoms there are, and so there's 1 carbon atom, and each carbon atom has a mass of 12 AMUs. Okay, CO2 has 2 oxygen atoms, and each oxygen atom has a mass of 16 atomic mass units. And so 1 CO2 molecule, which is 1 carbon plus 2 oxygen atoms, must have a mass of 44 atomic mass units. So we take the number of carbon atoms, 1, times the atomic mass unit of carbon, and to it we add the number of oxygen atoms, which is 2, and each oxygen atom is 16 AMUs, and we total them up, and we get that a CO2 molecule has an atomic mass of 44 atomic mass units. Now, if we want to convert that to kilograms, we just use our conversion factor, where 1 atomic mass unit is, did I mess that up? Oh, should be 10 to the negative 27, I'm sorry. So, typo here, this is 1.66 times 10 to the negative 27 kilograms per atomic mass unit. And when you multiply that by 44 atomic mass units, this answer is correct. You get that the mass of a carbon dioxide molecule is 7.30 times 10 to the negative 26 kilograms. Okay. Now, if we know the atomic mass of carbon dioxide, which is 44 atomic mass units, that means that 1 mole of carbon dioxide gas, or Avogadro's number of CO2 molecules, also weighs 44 grams. And so 1 mole of carbon dioxide weighs 44 grams. And so it's pretty easy. So just repeating again, we look at the periodic table and we can get the atomic mass of any element. Once we know the atomic mass, we also know that that numerical value is the molar mass, the number of grams in a mole. And if we want to go back and forth from atomic mass in AMUs to kilograms, we simply use the fact that each atomic mass unit is roughly the mass of a proton, which is 1.66 times 10 to the negative 27 kilograms. Okay. A couple more sips of your coffee to get you through the next section here. It's nighttime or I would get some. So if we know the mass and we know the volume, we can calculate the density of a substance. And the density is a measure of how packed in, how much mass per volume the substance has. And since if we go in terms of mass density, which is rho, we've already described this before, mass is in kilograms, volume is in meters cubed, and so the mass density typical units are kilograms per meter cubed. And if we look over here, we see that there's large differences. So for example, silicon, which is a solid, has a mass of 2,330 kilograms per meter cubed, whereas air at standard temperature and pressure has a mass of roughly 1 kilogram per meter cubed. And so silicon is about 2,000 times more dense than air. And solids are more dense than liquids, and liquids are more dense than gases, and that's just related to the fact that the bonds are tighter and the molecules are more packed in with solids than with liquids and with gases. Now, in terms that another way of describing the density of a substance is in terms of the number density. And instead of the mass per volume, the number density can be described in terms of the number of molecules per volume, so big N, number of molecules divided by V. Or it can be described in terms for gases. Often we describe it in terms of the number of moles per volume, where moles are little n, and this is moles per meter cubed. Now we know that molecules and moles are not SI units, and so the purist would say that this has units of 1 over meter cubed. I like to include molecules and moles on here just for dimensional analysis. It helps me. But you can do whatever one works for you. So the number densities for solids, typically in every cubic meter of space, there's about 10 to the 29 molecules for a solid. And it goes down, it's about 100 times lower for the gas, about 10 to the 27. Here I summarized some of the results in a table. We won't go over it right now, but it is here for you to kind of summarize the units that we use to describe mass and density. So none of this stuff is hard, it's just bookkeeping. And most of the time, including the dimensions in all of your answers and for each unit and doing dimensional analysis will usually guide you to the right answer, or at the very least tell you if you have the wrong units, if you divided when you should have multiplied. Here's a few more equations. So the best way, I think, to learn some of this is just by doing a couple examples. So let's start by calculating the number of moles in a 2 centimeter by 2 centimeter by 2 centimeter cube of copper. So we have a copper block, and each face is 2 centimeters by 2 centimeters. And we're given the mass of copper, so in every meter cube of copper, there's 8,920 kilograms, and we're given the atomic mass of copper is 64 AMUs, and that's just from the periodic table here. If we look up copper, it's really 63.5 AMUs, but we're getting a little lazy here, and I'm only using 2 sig figs in this example. That's my bad. So how do we do this? So we want to determine the number of moles. So stop your video and try it on your own before coming back. Click. All right, so I assume that you've tried it. So there's a couple different ways you can do it. So if we know the mass, if we know the density, we can multiply the density by the volume, and we can get the total mass. And that's how I'm going to do it. So I take the volume, multiply by the density to get the mass in kilograms. And once I know the mass, I know that the atomic mass is 64. So 64 AMUs is the mass of one copper atom. So first let's get the mass here. And so we know the density, 8,920 kilograms per meter cubed. You can either convert the mass from kilograms to meter cubes to grams per centimeter cube, or we can take the volume, which is in centimeters cubed, and we can convert it to meters cubed. Just for kicks, I did the former. And so I expressed the density. So the density is in kilograms per meter cubed. And I converted that to grams per centimeter cubed using my conversion factors between meters and centimeters and between grams and kilograms. And so the density of copper can also be written as 88.92 grams per centimeter cubed. And then I can just keep the volume as 2 centimeters by 2 centimeters by 2 centimeters. So that's 8 cubic centimeters, and I multiply by the density, and I get a mass of 71 kilograms, or 71 grams, sorry. I also could have just kept the density in terms of kilograms per meter cubed, and I could have took the 8 centimeter cubed volume and converted that to meters cubed, and I would have got the mass in kilograms. But either way, you're going to get the same answer. So the reason I did it my way and got the mass in grams is I know that 1 mole of copper is 64 grams, because the atomic mass of copper is 64, which means 1 mole is 64 grams. And so since we're trying to calculate the number of moles, I can take my mass in grams and I divide by 64 grams per mole, and I get 1.1 moles. And here's where keeping track of all your dimensions really helps here, because if I forget whether N is equal to M mole over M or M over M mole, I can just use the dimensions. I know I must have dimensions of moles, and so therefore I must divide grams by grams per mole in order to get moles. And so the number of moles in this substance, if there are 1.1 moles of copper in a 2 centimeter by 2 centimeter by 2 centimeter cube. Now, if I wanted to calculate the number of molecules, I would just multiply 1.1 moles times 6.022 times 10 to the 23 molecules per mole, and I would get the number of molecules. Okay, so just keeping track of your dimensions and dimensional analysis is usually a really good way of working through this problem. Otherwise, I can't remember most of these formulas. Okay, so just for fun, let's do another example. So in this problem, we're given that the mass density of aluminum is 2,700 kilograms per meter cubed, and we're given from the periodic table that the atomic mass of aluminum is 27 AMUs. So the question is, how many molecules are in each meter cubed of aluminum? In other words, what's the number density of the aluminum Okay, and there's a couple different, like most problems, there's multiple ways that you can do the problem, and so I'm going to illustrate 2 different ways. So the first is I can calculate, I want to go from, so we can go from grams, we want to go from kilograms per meter cubed, and we want to go to the number of molecules per meter cubed, okay, or 1 over meter cubed. So you can see that we have to get rid of kilograms, right? We're starting off with kilograms per meter cubed, and we want to go to atoms per meter cubed, I'm sorry. So we need to get rid of kilograms. And so if we divide this number, just using dimensional analysis, 2,700 kilograms per meter cubed, and we can calculate how many kilograms per molecule and divide, we would end up with molecules per meter cubed. And that's exactly what we're going to do. So we need to calculate how many kilograms are in a given molecule. Well, I keep saying molecule, but aluminum's atom, sorry. So aluminum has an atomic mass of 27 atomic mass units, and each atomic mass unit is 1.66 times 10 to the negative 27 kilograms, and so we can get that one atom of aluminum weighs 4.48 times 10 to the negative 26 kilograms. And then if we divide kilograms per molecule, per atom, kilograms per meter cubed divided by kilograms per atom, we get atoms per meter cubed. Okay. And here's another example where I can't remember a lot of these formulas off the top of my head, but you start by taking what you're given, kilograms per meter cubed, and I apply dimensional analysis. I want to go to atoms per meter cubed, and so I know I'm going to somehow need to divide by kilograms in order to get rid of that. And so that's what I did here. So you can either write down all these formulas, or often you can use dimensional analysis. I hate to beat this to death, but it saves me quite often to go from one to the other. Okay. The second way to do it, I think, is a little more difficult, but I'm including it for completeness. So the first method, too, so you can calculate the number of moles of aluminum in 1 cubic meter, and then I know that each mole corresponds to Avogadro's number of atoms, and so we can do that. So we can use the fact that the molar mass of aluminum, aluminum has a mass of 27 AMUs, so there are 27 grams of aluminum in every mole. And so I can take the mass in a kilogram, 2,700 kilograms, and I know that there's 27 grams per mole, and so I can get the number of moles, and then I can multiply by Avogadro's number to get the number of molecules, and I get the same answer, except for a little bit of a rounding error, that I got in the previous problem. So as with many of these problems, there's multiple ways to do the problem. In this particular example, I personally think it's a lot easier to just divide by the mass per atom, but you can do that either way. Oh, now I really need a coffee, but so we're done with that, going back and forth between different mass units. The next topic that we need to cover is temperature. And we'll see in the subsequent chapters that temperature is basically a measure of the kinetic energy, the average kinetic energy of the molecules or atoms. And so higher temperatures, the molecules have more kinetic energy. They're moving around faster. They're smashing into the walls of their container, and that's a higher temperature. Lower energy, the molecules or atoms are moving slower. They don't have as much thermal energy. And so at the molecular level, then, temperature is a measure of the kinetic energy. So what properties depend on temperature? Well, length, volume, right? Substances expand as they heat up. We'll see that shortly. The amount of radiation emitted by a body, for example, the sun, depends heavily on its temperature. And so a lot of properties depend on temperature. for an ideal gas under certain conditions, the pressure depends on temperature. Higher temperatures for a given number of molecules, they'll have more kinetic energy. They'll smash into the walls of the container harder, and they'll exert a greater pressure on the container than at lower temperatures. Before we go into all of this, we're going to go into the different units that we can describe temperature in. You've seen all these units most likely, so this should be a review. Another sip of coffee, maybe. So there's the two scales that are most commonly used are the Celsius scale and the Fahrenheit scale. And they both make use of 2 points. They both make use of the boiling point of water and the freezing point of water. And they use this to define their scale. And so the first point, the boiling point of water, on the Celsius scale, that is given a value of 100 degrees Celsius. On the Fahrenheit scale, the boiling point of water at sea level, or the temperature at which water boils at sea level, is 212 degrees Fahrenheit. And so since this is the same temperature, it's the boiling point of water, 100 degrees Celsius must be the same as 212 degrees Fahrenheit. They're just different scales. The other point that's used is the freezing point, the ice point of water. And on the Celsius scale, this is assigned a number of 0, so the freezing point of water is 0 degrees Celsius. And on the Fahrenheit scale, this value is assigned the number 32. So 32 degrees Fahrenheit must be the same as 0 degrees Celsius, and 100 degrees Celsius must be the same as 212 degrees Fahrenheit. So these 2 points define our scale for each type of units. Okay? And if we know this, then we can if we know the value in units of degrees Celsius at any temperature, we can convert to Fahrenheit. So the Celsius scale takes these and breaks it into 100 units in degrees Celsius, and the Fahrenheit breaks these same 100 units into 180 units, 212 minus 32. And so each step up and down of 1 degree Celsius must correspond to stepping up or down 1.8 degrees Fahrenheit, because we have to make 100 steps to get from the freezing to the boiling point for Celsius, and we must make 180 unit steps on the Fahrenheit scale to get from freezing to boiling. And so each degree Celsius change in temperature must correspond to 1.8 degrees Fahrenheit. And we can define this, we can take to convert it into a mathematical equation, we can say that if we know Celsius, we add 32 degrees. The boiling point, or the freezing point in Fahrenheit is 32 degrees. The freezing point in Celsius is 0. So the degrees Fahrenheit is 32 plus the scale factor 9/5 times the number of degrees Celsius. And we can invert this to go from Celsius to Fahrenheit. Now you can write down this equation. Another way of doing it is just to start at the freezing point, and for every 10 degrees that you go up or down on the Celsius scale, we must go up or down 18 degrees Fahrenheit. Or for every 5 degrees Celsius, we must step up or down 9 degrees Fahrenheit. So let's do an example. So a healthy person has an oral temperature of 98.6 degrees Fahrenheit. Mine is like 97.4, so I must be unhealthy. So what would this reading be on the Celsius scale? Well, we can either use our formula right here, and we can write 98.6 degrees Fahrenheit We can subtract off 32 and we get 66.6 degrees Fahrenheit. And we can multiply by 5/9 and we get 37 degrees Celsius. An equivalent way of doing it is to say that 98.6 Fahrenheit is 66.6 degrees above the freezing point. And so each degree Celsius is 9.5 degrees Fahrenheit, and that's 37 degrees above 0 degrees Celsius, which is 37. So it's mathematically the same thing. It's just apples and oranges, different ways of doing it. So here's another example. Suppose that you know that the temperature is negative 20 degrees Celsius. To find the temperature in Fahrenheit, we can either just plug and chug. We can put negative 20 in, and we can multiply by 9/5, and I get negative 36. And then I add 32, and it's negative 4 degrees Fahrenheit. An equivalent way of doing it is to say that I start at 0 degrees Celsius, which is 32 degrees Fahrenheit, and every 10 degrees Celsius that I step in one direction is 18 degrees Fahrenheit. So 0 degrees Celsius is 32 Fahrenheit. Negative 10 Celsius must be 18 below 32, which is we're down to 14 Fahrenheit. Negative 20 is another 10 degrees Celsius, which is another 18 Fahrenheit, and we're down to negative 4 degrees Fahrenheit. So it's the same thing. It's just you can either remember the formula or do it this way. But mathematically, you're doing the same thing. A third scale, which is often used in scientific calculations, is what's called the Kelvin scale. In the Kelvin scale, the step size is exactly the same as the Celsius scale, except that you add 273.15 to the Celsius value to go from Kelvin. So, for example, 0 degrees Celsius is 273.15 Kelvin, and absolute 0 degrees Kelvin is negative 273.15 degrees Celsius. And we'll see later in the course that there is no such thing as absolute 0 Kelvin, because at the microscopic level the atoms are always moving a little bit, and so the temperature is never exactly 0 degrees Kelvin. Okay. So here I summarized converting between the three temperature scales. You'll get some homework problems. Again, there's nothing conceptually difficult about this. It's just bookkeeping. And another nomenclature, little thing here with nomenclature, you notice we didn't put the degree symbol above Kelvin. It's just you refer to the number as 273.15 Kelvin, or K, instead of degrees Kelvin. So the last thing that we'll go into in this lecture is we're going to go into some ways of measuring temperature. And most methods for measuring temperature, most thermometers, make use of the fact that the length or the volume of a material or a substance changes with temperature. And this will get us into thermal expansion. And so if we know, for example, how much a given substance changes with every degree Celsius or Fahrenheit, we can put marks on the thermometer and we can measure the amount at which a fluid expands or contracts, and we can use that, for example, with a bulb thermometer to get the temperature. There's electronic devices, thermocouples and thermistors and platinum resistance thermometers, which make use of the fact that the material properties change with temperature, the electrical properties, and they can use that to measure temperature. So for example, a platinum resistance thermometer often called an RTD, resistance temperature device, makes use of the fact that a platinum wire changes in a very precisely known manner. The length changes with temperature in a very well-known manner, and the resistance changes with length. And so we can calculate changes, we can convert changes in resistance to changes in temperature. Here's what's called a thermocouple. These are often used in furnaces, in many other places, and these just make use of the fact that the the length of two dissimilar materials changes in a different manner with temperature, and you get a voltage difference. So how do we quantify thermal expansion? Well, let's take an example here. So you have an object, and suppose we measure its length L0 at some temperature T0, and suppose it expands by an amount delta L as the temperature changes by an amount delta T. And most materials, when heated, expand, and so for most materials, as temperature increases, the length will increase by some amount delta L. Well, it's known experimentally that the change in length is proportional to the change in temperature, as long as it's not too large. So, example, if we double the change in temperature, if we heat something up by 2 degrees Celsius instead of 1 degree Celsius, its length will change by twice as much than it would if we just increase the temperature 1 degree Celsius. So the change in the length is proportional to the change in the temperature. It's also proportional to the original length of the object. So for example, a 10-meter rod is going to expand much more for a given 1 degree Celsius change than a 1 meter rod. And so it depends on its initial length, the change in length. And the third property, it depends on the property of the material. And this is a material property called the thermal expansion coefficient or the linear expansion coefficient. And since delta L has units of length, meters, and L0 has units of meters, and change in Celsius is change in temperature is 1 over degrees Celsius, then alpha must have units of 1 over degrees Celsius. And to see what this alpha means, this is a material property, we can divide both sides of this by L0, and we can divide both sides by delta T to get alpha alone, and alpha is equal to the fractional change in the length of the material for every 1 degree Celsius change in temperature. Okay. And so that has units of 1 over degrees Celsius. And so here's some examples. For aluminum, alpha is 2.3 times 10 to the negative 5 per degree Celsius, which means that the fractional change in the volume is 2.3 times 10 to the negative 5 for every 1 degree Celsius change in temperature, delta L over L0. The fractional change is 2.3 times 10 to the negative 5, or 0.0023%. And you see that materials such as aluminum tend to expand more. Steel expands only half as much as aluminum. So if we heat aluminum up and we heat steel up and we increase both of their temperatures by the same amount, the length of a steel rod will only increase about half as much as the length of an aluminum rod. And then you get some materials like Invar, which have low thermal expansion coefficients. They tend to expand less. And so different materials for the same length and the same temperature change will expand at different rates. And you'll be doing this, I believe, in Lab 3 in a few weeks. Now with gases and with liquids, we need to talk about their volume expansion coefficient instead of the length, because you have expansion in all three dimensions. You actually do with length too, but length is less defined with gases and liquids. So let's again, it's as with other cases, it's easier to do an example here. So suppose we have a concrete sidewalk, and it's constructed between two buildings, and suppose that we constructed it on a day when it's 25 degrees Celsius, and suppose that there was no space in between, there was no gap provided to let these sections expand when heated. And suppose, so there's no air, there's no gap in here that was built in here, as there should be. And so the question is, first of all, if each of these concrete slabs is 3.0 meters, and they're butted up against one another, the first question is, by how much is each of these slabs going to increase its length? How much is each one going to expand by if the temperature rises to 38 degrees Celsius, which is about 100 degrees Fahrenheit? So we're going on a day where it's about 77 degrees Fahrenheit to a day when it's about 100 degrees Fahrenheit. And so the question, first one, is how much is each one of these slabs going to expand? And then the second question is, okay, well, they're expanding, but there's nowhere to go because there was no gap built in between them. And so what's going to happen is that the slabs are going to push against each other, and they're going to rise, and they're going to buckle. And so the question is, what is the vertical distance that each slab is going to buckle? Okay. So first, we can just plug and chug here. Each slab has a nominal length of 3.0 meters. The temperature change is positive. It's 38 degrees minus 25 degrees, and so delta T is positive 13 degrees Celsius. And we go to our table and we look up that concrete has a linear expansion coefficient of 1.2 times 10 to the negative 5. So we plug that in per degree Celsius. Oh wait, I'm sorry. I might have screwed up here. This should be 10 to the negative 5 here. My bad. The answer's right. Oh, that's right. That's the same. It's 12 times 10 to the negative 6, which is 1.2 times 10 to the negative 5. Maybe I need more coffee. So we multiply that, 12 times 10 to the negative 6 per degree Celsius, times a nominal length of 3 meters, times the temperature change of 13 degrees Celsius. And so each slab increases by the length increases by 0.47 millimeters. Sounds like a small amount, but it is enough to cause buckling. And so the new length of each slab is the original length, 3.000 meters, plus 0.47 meters is 3.00047 meters. Okay? And so now you have a situation like this, where now the slabs are going to push against each other, they're going to buckle, they're going to rise like this. And the question is, what's the vertical distance here that it's going to buckle by? And so to do that, we use Pythagorean's theorem. We know it's 3.00 meters is the length when there's no expansion, and the new length is 3.00047 meters. And so we can take Pythagorean's theorem, and we get that it'll buckle by an amount 5.3 centimeters, which is a little over 2 inches. And so they'll rise by a little over 2 inches. And so this was not a very well-engineered project, and that's why you need to leave expansion, air gap in there to expand when heated. Here's another example of a bimetallic strip, and this is often used in switches. So this here you put two dissimilar metals and you weld it together, and this one is brass and this one is steel. Okay, so what's going to happen when they're heated? Well, brass expands more than steel when heated, and so when the temperature increases, the change in the length of brass will be larger than steel, and so this, when heated, this will curl to the right. Similarly, when it's cooled, the length of brass will decrease more than the length of steel, and so when it's cooled, it will curve to the left. And so this strip curves either to the right or the left, depending on if it's heated or cooled. Here's an example of how it's used to switch on and off the heating element in a coffee pot. So here you turn it on and it's cool, and so the switch is closed. When the switch gets hot, the strip curls and it breaks contact here. And when it breaks contact, the electricity doesn't have a complete loop to flow around, and you get an open circuit, and it turns off the heater. And so there's several examples of where these bimetallic switches, where they basically turn on or off. They curl one way or another depending on if you're cooled or warmed. So this is enough for today. And I'm getting sleepy. So I think we will end the lecture now, and we'll continue with thermal expansion in 3 dimensions tomorrow, and then we'll move on to ideal gases. Hope the coffee kept you awake. Have a good day.